Swayam Prabha. Digital India. Educated India.
We were discussing about surface tension driven flows, and we brought into discussion one very important aspect, that is surface tension driven flow of blood. And to understand that how do we model the surface tension driven flow of blood, we started discussing a little bit about the rheology of blood, that is the constitutive behavior expressed in terms of some mathematical model. So, we suggested that there could be several complex models of blood rheology, but at the same time for simplicity we prefer to use a model like this, where K and N are the two parameters consistency index and behavioral index. Now, these indices, unlike many other fluids, are not constant for blood, and these indices sensitively depend on the composition of the blood. So, see, I am trying to give you a broad picture. Let us say that somebody is handling a diseased blood sample, that means a blood sample that carries the signature of a disease. Now, there are several diseases in which, because of the disease, there will be alteration in the blood rheology, and these parameters K and N will change, and if these parameters K and N change, the fluid flow characteristics will change. So, if you have a micro channel or a micro capillary through which blood is being transmitted and the flow characteristics of the blood are changing, then that might give an indication of the existence of a certain disease in a blood sample. So, that is many times critical, and let us see now that what are the parameters on which this will depend. So, as I pointed out in the previous lecture, that the T stars can be neglected under certain situations. So, T is equal to K S to the power n, where this T and S we have discussed, these are stress and rate of deformation dyadic of dyadics. Now, this K and N, these are again dependent on several parameters. One of the important parameters is called the hematocrit fraction. Hematocrit fraction is essentially the volume fraction of the red blood cells. So, it will depend sensitively on the volume fraction of the red blood cells, because we see here that the K depends on the H is the hematocrit fraction. So, in some way, see, these are not in medical applications, see, medical applications are very complicated. So, you do not always expect that equations and expressions will be derived from first principles. So, these are the expressions for K and N which are given here, these are not derived from first principles, but these are curve fitted from a huge number of experimental data collected over the years. So, I mean, in that spirit you need to understand, I mean, there is no like first principle proof of, right, I mean, where from these expressions come. So, we see here that some coefficients C1, C2, C3 appear in this context, and before getting into what should be C1, C2, C3 on what parameters those will depend, let us quickly revisit the blood properties. So, human plasma is transparent, plasma is the watery part of the blood that is transparent, slightly yellowish with a typical density of a typical 1035 kg per meter cube. So, it is like you can understand that it is just like water density. It contains a solution of plasma proteins in an aqueous medium. Proteins contain about 7% of the total plasma volume and can be classified into 3 major groups: albumin, globulin and fibrinogen. We discussed about fibrinogen and its importance in the context of the constitutive behavior, that if you take away the fibrinogen, the T star component will go away. Plasma also contains the emulsified fats or lipids, cholesterol, free fatty acids, hormones, dissolved oxygen, dissolved carbon dioxide. So, this is the plasma composition. Now, whole blood is plasma plus the blood cells. So, blood cells will contain red blood cells, erythrocytes. Red blood cells are also called as erythrocytes. So, you can see like how the red blood cells typically look in these pictures. WBCs or the white blood cells, which are also called as leukocytes, and platelets in an aqueous solution. The red blood cell count is approximately 5 million per millimeter cube, which is about 40 to 45% by volume of the whole blood. So, as I told you that we define a parameter H, which is hematocrit. If you express this hematocrit by volume percentage, then it is about 40 to 45%, but you can well understand that it is not constant. It will vary from one individual to another individual, it will vary from one diseased condition to another diseased condition. So, based on the hematocrit, it is possible to like describe the rheology of the blood sample. Now, just to give you some idea, typical dimensions of RBC, typical